We will now discuss the processes that take place when electromagnetic radiation interacts with matter. When electromagnetic radiation interacts with matter, several phenomena can take place. They provide information on the biological system under investigation. The phenomena are scattering of electromagnetic radiation, absorption of electromagnetic radiation, emission of electromagnetic radiation, and photochemical processes, which are chemical reactions that take place in an electronically excited state. We start with light scattering, or more general, scattering of electromagnetic radiation. Scattering changes the direction of propagation of an electromagnetic wave. This is illustrated in the figure on the left, where a biomolecule is hit by incoming electromagnetic radiation from the left. The scattered radiation is shown here, and it can be clearly seen that the direction of propagation has changed. In contrast to what is shown in the illustration, light is generally scattered in all directions. The energy of the photons may or may not change in the scattering process. If there is no energy change, we speak of elastic scattering, and the process is called Rayleigh scattering, after the English physicist Lord Rayleigh for his discovery of the effect. This is by far the most frequently occurring scattering process. If the photon energy changes in the scattering process, we speak of inelastic scattering. One prominent example for this is Raman scattering, which is named after the Indian scientist Sir Raman, who discovered the effect. After scattering, the photon energy may be smaller or larger than that of the incident photons. The figure on the right shows a spectrum of scattered light. The horizontal axis can be wavelength, wave number, or frequency, but here I have chosen to use the photon energy, which is proportional to frequency and wave number. The vertical axis is the intensity of the scattered light. The large majority of photons is scattered elastically and gives rise to the huge Rayleigh peak. Remember that the position of the Rayleigh peak indicates the photon energy of the incoming photons. Left and right to the Rayleigh peak, we find the Raman peaks. Those to the left correspond to photons which have less energy than the incident photons, and those to the right correspond to photons that have more energy. Note that scattering processes with energy loss are more probable than scattering processes with energy gain. This will become clear when we discuss Raman spectroscopy. Scattering is part of our everyday life. For example, the sky is blue because there is scattering. Without scattering, we would see the sunlight only when we directly look into the sun. The rest of the sky would be black. But because sunlight is scattered by particles in the atmosphere, we see scattered sunlight when we do not directly look into the sun. This light is blue because blue light is scattered more than light with longer wavelengths. This is also true for experiments. If you want to observe light scattering, then it is advantageous to turn to short wavelengths, UV light or blue light, because this will increase the intensity of the scattered light. On the other hand, scattering can also be a problem in spectroscopic experiments, and this is most pronounced in the UV spectral range. Another example for everyday light scattering phenomena are the appearances of milk or an oil-water suspension. They are turbid because light is scattered from small fat or oil droplets. Scattering can be explained as follows. the electric field vector of the electromagnetic wave induces oscillations of the charges in the atoms. In this illustration, the electric field vector oscillates up and down. The nuclei are shown in blue and the electron cloud in red. The nuclei are much heavier than the electrons, so the nuclei will be moved much less than the electrons. The figure shows how the electron cloud moves up and down with the oscillating electric field. The oscillating electrons create an oscillating dipole, which acts like a small antenna and emits radiation in all directions. The emitted radiation from an atom superimposes with that of all other atoms and with the incident radiation. Therefore, scattering is the explanation of the phenomena reflection and refraction. Reflected light is the superposition of the scattered light from all atoms, and the phenomenon refraction is the result of the superposition of the incident wave with all scattered waves. The second process that we want to discuss is the absorption of electromagnetic radiation. In our illustration, we can see that the transmitted light wave has a smaller amplitude than the incident light, which means that it appears less intense. Some of the loss can be explained by scattering, as we just heard. The remaining loss is due to absorption of electromagnetic radiation by matter. In the photon view, the explanation is simple. Some of the incoming photons are absorbed, which lifts the absorbing substance to a higher energy state. The figure on the right shows an absorption spectrum. It is plotted against the wavelength. The vertical axis shows absorbance, which is a measure of the strength of absorption. As you can see, electromagnetic radiation is only absorbed in specific regions of the electromagnetic spectrum. In some regions we have strong absorption, in others weak or no absorption. The curves in the region of absorption are called absorption bands. They can be narrow or broad. When they are well separated, we call them resolved. Here are two well-resolved absorption bands. One is here, the other one is here. In contrast, on the right-hand side, we have several overlapping bands. The maximum of the band to the left is clearly seen, so this component band is still resolved. In contrast, the component band to the right is not resolved. It overlaps so much that its presence only generates a shoulder in the spectrum. The third process is emission of electromagnetic radiation. Emission can only occur from an excited state of a substance. Upon emission, the substance returns to a lower energy state. For example, light can be emitted from a hot body, like in an old-fashioned light bulb, or it can be emitted after light has been absorbed. In the latter case, the emitted light has a lower energy and longer wavelengths than the absorbed light. This has been exploited by washing powder producers to generate the whiter-than-white effect. They add an optical brightener to the washing powder that stays on the clothes after washing. It does the following trick. First, light in the ultraviolet region of the spectrum is absorbed. We cannot see UV light, so we do not realize that some of the UV light is absorbed. After absorption, light is emitted, but the wavelength of the emitted light is in the visible region. Therefore, more visible light radiates from the clothes than without optical brightener, which makes your t-shirt look brighter. The process just described is an example for the phenomenon of fluorescence, which we will discuss in detail in the fluorescence lecture. Finally, we turn to photochemical processes. For these to happen, a molecule must be in an electronically excited state. The excited state can be reached by absorption of photons with relatively high energy, which are those from light in the visible and ultraviolet spectral range. In the excited state, reactions can occur that do not take place in the ground state. Examples are rotations around bonds, which are double bonds in the ground state. Because of the double bond character in the ground state, such rotations do not occur in the ground state. Electron transfer reactions. Electrons in the excited state may be less tightly bound than in the ground state, and may therefore easier be transferred to electron acceptors nearby. Bond breakage. Some bonds are weaker in the excited state and can therefore easier be broken. An example for this are deprotonation reactions. Deprotonation may be facilitated in the excited state because the pKa value may be lower in the excited state than in the ground state. Photochemical effects are very important in biology. An example is the membrane protein bacteriorhodopsin, which we will meet again a bit later. It pumps protons and generates a proton gradient that is then used for ATP synthesis. The energy for this active transport process is provided by the absorption of a photon. Absorption leads to an excited state in which rotation is possible around a particular bond. This induces a number of structural changes in the protein that lead to proton transport. A further example is photosynthesis, where the initial process is the abstraction of an electron from a molecule in an excited state. This leads to a cascade of electron transfer reactions that result in the build-up of a proton gradient that is again used for ATP synthesis. Summarizing, we have discussed 4 processes that occur when electromagnetic radiation interacts with matter. These are scattering, absorption and emission of electromagnetic radiation, as well as photochemical processes.